So let's go ahead and take a look at the first concept we have to worry about here, and that is homeostasis. So, homeostasis is the basis for understanding physiology. Without understanding homeostasis, we can't really understand any of the other aspects of physiology that we're going to be looking at. Some of the things we have to worry about as it relates to homeostasis is the fact that it's dynamic. It's never a static situation. We're always fluctuating our ability to balance based off of all of the stimuli that are impacting us throughout the day. What we're attempting to do with our responses to all of these stimuli is allow for optimal functioning. And that optimal functioning is going to vary based off of what we're looking at attempting to do. So in class, optimal functioning would be you acing an exam, or you learning all of the intricacies that you need to learn in order to apply what you're trying to learn to whatever job you're looking at doing. Whereas if you happen to be an athlete, your optimal functioning is being able to have your maximal performance at that instant. If you're a patient, your optimal functioning, however, is returning back to simple normal homeostasis, the ability to get back to being healthy. The way in which homeostasis comes about developing is based off of a variety of reactions and interactions that are being placed upon it. The end result of all of this interaction is the ability to survive, where anything that is abnormal within the responses leads to a dysregulation, DYS regulation, and a diseased state. The way in which we're able to maintain and get to this delicate balance is through a host of regulatory mechanisms. The regulatory mechanisms we refer to as being feedback. There are two principal types of feedback mechanisms, and we'll get to those two principal types here in a second. When we talk about mechanisms, we have to look at where is this maintaining of homeostasis taking place. And this is where we have two distinct concepts that sound similar, but they're actually different. This is where we get the concepts of regulation versus the concepts of control. Control is within a biochemical pathway and is performed within a single pathway feedback, whereas regulation is systemic and is going to involve multiple biochemical pathways at multiple cells and multiple tissues. This is usually going to involve hormonal or cytokine signaling that are going to turn on and turn off enzymes at various cells to instigate responses necessary to get back to homeostasis. Whether we're looking at regulation or looking at control, the means by which we can go about doing this is through what's referred to as regulatory feedback. There are two types of regulatory feedback. There's what's referred to as positive feedback and what's referred to as negative feedback. Positive feedback is where each step that comes before it gets accentuated, where negative feedback is where each step that comes before it gets reduced. Opposite of feedback is what's referred to as feed forward. Feed forward is where we get accentuation after accentuation after accentuation. That is where the initial stimulus is triggering more of the initial stimulus. Whereas with feedback, we're trying to eliminate the stimulus from being there. The way in which this functions is based off what's referred to as upstream and downstream. And that's where we have to look at the cascade of events that are taking place within metabolism as a river, where things are constantly moving downward from step 1 to step 2 and step 2 to step 3 and step 3 to step 4 through the processes. If the step comes earlier, it's deemed upstream. That is, step 1 is upstream from step 2. If it occurs later, it's referred to as downstream. That is where step 100 is downstream from step 50. And what we do is we look at these pathways as a cascade of events where we have the initial stimulus and then the terminal effect with all of the various effects and affects occurring so that we have the most optimal response for the stimulus to allow for either survival or adaptation. The way in which feedback is going to ultimately affect homeostasis is that it's going to, one, eliminate the initial signal or stressor, and then two, make sure that the responses that we have is appropriate to the stressor if the feedback is negative. In the case of homeostatic disruption or homeostasis disruption, anytime we say signal, we are talking about a stress. And since we're talking about stress, we'll call it a stressor. We can examine these stressors either as what's referred to as an autoregulatory response, that is, the cell itself is going to change its function based off of the stress that's occurring. That is the idea of control. Or we can look at it based off of a systemic response where we have either neurological signals or neuroendocrinological signals, cytokines, hormones, neurotransmitters that come into play based off of the concept of regulation. When we look at feedback, we have the two general types. We have negative, and the whole idea of negative is where we are going to have the downstream effects going to slow the upstream effects. Whereas the positive is where the downstream will actually accentuate the rate of the upstream. With negative, we are trying to get the optimal level of responsiveness, whereas with positive, we are trying to get the maximal level of responsiveness. We look at this feedback in two ways. First way is based off of what's referred to as the sensory pathway. This is where a stimulus leads to reception, reception leads to integration, integration leads to response, response leads to effect to hopefully eliminate the stimulus, or by the biochemical pathway, where reactant A interacts with its enzyme to form metabolite B, metabolite B interacts with its enzyme to form metabolite C, metabolite C interacts with its enzyme to form metabolite D, at which point in time we finally form a product from the initial reactant. In this pathway, we can look at it in terms of either the positive or the negative. So in negative feedback, what we're attempting to do is we're attempting to minimize what is being built so that we have the optimal amount being built. So as A interacts with its enzyme, it's forming B. As B gets formed, it slows down both how the cell uptakes A and the rate at which enzyme A is functioning. As B gets formed, it's going to interact with its enzyme to form C. C is going to slow down the rate at which B starts to form C, but it's also going to slow down the rate at which A starts to form B, so that we have the optimal amount of C being formed. As C gets formed, it's also going to interact with its own enzyme to start forming product D. Product D is going to do the exact same thing. It's going to slow down the rate at which it's being formed by slowing down the rate at which enzyme C is functioning, also by slowing down the rate at which enzyme B is functioning, also by slowing down the rate at which enzyme A is functioning, all in an attempt to ensure that we have the optimal amount of product D. Opposite of this, we have positive feedback, where we have the same reactant coming in. It interacts with its enzyme to start forming B. The cell says, I want to have as much B as possible. I want to maximize B. So I'm going to stimulate additional A uptake and stimulate additional A reaction. As B gets formed, it's going to interact with its enzyme to form C. The cell says, I want more C to form. And so it's going to go about accentuating and stimulating all of the things that come upstream. As C is formed, it interacts with its enzyme to form D. Once again, the cell wants to have as much D as possible. It wants to maximize the amount of D. Since it's attempting to maximize the amount of D, it's going to stimulate everything that comes before it so that we have as much D as the cell can possibly have. In the positive feedback, we're not worried about the immediate response. We're worried about survival. Whereas with the negative feedback, we're worried about survival. We're worried about being able to have the correct or optimal response so that not only do we survive this stress, but we're better set up to survive the next stress. So why are we going to have negative feedback? It's going to ensure that the stressor signal is controlled and regulated properly. It ensures that tissues are going to be responsible for the response to the stressor and don't go into dysregulation. Eliminating the stressor can lead to an excessive response. It limits the excessive response by slowing the rate of response. By doing this, it ensures the response does not trigger disruption in the other direction. So what ends up happening, if we look at this, we go from having not enough to too much, to just right, to too little, to just right, to too much, to just right, to too little, and we constantly are swinging right around the optimal line. One of the ways you can think about this negative feedback is kind of like Goldilocks, where the idea here is through negative feedback homeostasis, we're able to be baby beared. Why do we get positive feedback? We get positive feedback because we are constantly under a response to stress. We get positive feedback to amplify the responses to eliminate the stress. It allows for acute survival without the worrying about the long-term ramifications. It's simply worried about getting rid of that stress. The problem with this is that it can cause dysregulation. It can cause dysregulation by getting too much to be way too much. And when we get way too much, as we'll talk about when we talk about neuroendocrine physiology, it could actually block the endocrine functionality from taking place. If we combine the positive feedback allowing for survival with the negative feedback of ensuring that we don't have too much or too little, we can get long-term adaptations. These long-term adaptations you can think about kind of like the story of the three little pigs, where we're going to constantly be redefining what our response to the stress happens to be until we can survive the stress.